Hey, it's Kirsch. In this video, I'm going to show you how I do a quick circuit simulation for stability, just like any working engineer would in their simulation software. The technique is to inject a small AC signal into the feedback loop of your power switching converter, in our case, the flyback converter. What's going to happen is when we plot the phase and the gain of that AC circuit, we get a very good idea of how it responds to errors in the output voltage and changes in that error. We also get a strong sense of how it will respond to sudden changes in current demand at Vout load. This is going to let you know the likelihood of the circuit ringing, and it does all of this in one simulation instead of brute forcing it with hundreds of transient simulations. So with this AC simulation, it gives you data you can trust. So here I've taken a modified reference design from Texas Instruments just to demonstrate the feedback behavior in the AC analysis. If we go to our AC setup, I'll show you what settings you need to use. First of all, you're going to want to use the averaged model for a chip, not the transient model, to do this analysis. So I got an average model of our same chip from our other flyback circuit where we had the transient model. And we don't need to model like different switching, like a whole switch power supply. Within this average model, we have this information. Okay, so the pinouts are different. There are some adjustments. And here I want to bring your attention to our Middlebrook injection. What this does is it inserts that little AC signal into the circuit and then checks what the response on the output voltage is like. That's all, pretty much, across different frequencies. Just how much gain or boost in the signal does the controller do, when it gets a signal into the feedback, that little AC signal into feedback, how does the controller respond? How much does it boost by? And when does it start cutting off? Like when you at a certain frequency, you're going to reduce how much gain you're giving that signal in the feedback. Okay. And that frequency is sort of like a bump or a cutoff frequency. And also, let's talk about phase. Phase is where it's like how much margin do you have so that the controller doesn't flip the polarity of the error signal, of the signal that it's getting from the error. If it flips the polarity, then it's going to start adding more error to your problem. Okay, so we want to stay away from 180 degrees. I'll show that to you. So let's go ahead and set up the simulation. In my simulation setup, you're going to want something like AC sweep noise, not transient. Okay, AC sweep. And general settings checked. Logarithmic, where we have decade. Then start frequency at 100. It could be 10 hertz, whatever the case is. End frequency, type in however amount, meg or mega. Then you have points per decade. We're going to do 1,000 points per decade, relatively high resolution, and that's all you need. For your configuration files in the library, make sure that your .lib file for your average model is inside that configuration file, add it to design. Any other settings, you can pretty much keep the same. Notice here for data collection, we have the voltages and currents set as all but internal circuits. The rest, like power, digital, noise, we don't need those unless you're doing a noise analysis. Now that everything's set up, we're ready to run the simulation. Hit the run button or F11 on your keyboard, and then you'll see your output. Specifically, I want to look at V out over V feedback. That is this output node or net, where it says V out, over the feedback, okay? So that we see what the response is on the V out with respect to any changes that slip in through here in the AC signal and this net. We can see any changes on the feedback and how much of a change there is in the ratio of V out to V feedback. Now let's look at our results. Look at this. The V out over the V feedback goes and it decreases. It has a certain amount of gain, which is what we want, right? As long as we are operational, we want to amplify that error and to notice when that's there so the controller can execute a certain gain to get our V out. Basically what the gain does is let me explain this. What the gain does is it multiplies or amplifies and says, hey, we have a certain error. We're going to put out this much gain to increase the duty cycle or the on time for the switch. So we're going to keep the switch on a bit longer. And because that switch being on longer is going to increase our output, or it's going to increase the amount of energy that we dump into the primary side inductor, which gets stored in there, and then it gets released to the secondary side inductor once the switch is turned off. Okay, and then that gets released and whatnot. So now that's the gain response. Notice how it starts to go down to 0, meaning a gain of 1 essentially, and decreases further. Now let's look at the phase. So it's doing its job in terms of gain for error, but let's look at phase. What does this mean? This means if I were to take my 0D frequency here and then look at what that means in terms of the phase, I could see how delayed it is when I get a certain gain or a certain error that I'm amplifying. Is it overly delayed? Is it early? Whatever the case is. And this lets me know that as long as I'm far enough away from 180 degrees being out of phase, meaning let's say I get an error and I want to amplify and I want to increase the duty cycle. Well, when you're 180 degrees or super late, or when you're super late when it comes to the changing the gain or changing the duty cycle on time, if you're 180 degrees out of phase, what you're going to do is decrease the duty cycle and increase the error, or vice versa. When you're supposed to decrease, you increase the duty cycle. That's not great. What that's going to do in extremely short amounts of time is blow up your converter, okay, or overstress it, or make it get extremely hot and possibly blow up. All right, so that's why we totally want to stay far away from 180 degrees. Once we know we're far enough away from that, then that means we have a lot of margin, a lot of space where we can get that boost in that gain all the way down to minus 16 dB, and we're still fine in terms of loop stability. Now, if it was the case where our 0 dB crossover was really close to 180 degrees, then we would have a problem. By really close, I mean anything less than 30 degrees close. So if you're down to like 150 degrees by that crossover frequency, you could be cooked, okay? What that would look like is it may start the controller, because the phase is so close to 180 degrees being out of sync, it may become underdamped. You may get oscillations on your output voltage instead of it having a quick little ripple and having pretty much 0 oscillations or just a small ripple. But you can get oscillations if your phase is too close to 180 degrees, right? And if your gain isn't large enough and whatnot, so forth. So you really need to check that. It's that phase that will determine or show you the real stability in that loop just from one AC analysis. That's all I wanted to show you to explain how this loop stability and AC sweep analysis works and how it's just a faster way to determine or get a real accurate idea of stability. So test it out on your transformer or on your flyback or switch mode power converters and then see what you get. If you can get an average model for your chip, even better. We'll be carrying these settings into the design guide everywhere from placement optimization, hot loops in the circuit, PCB layout optimization, keep outs, clearances. That way, what we get in simulation will match once we get to PCB layout as well. Now that you know more about the importance of AC sweep analysis, even for switch mode power supplies, you can determine loop stability in seconds, not hours. All right, have a good one.